stuff up. So here we go. Ready? There we go. Let's start one. Biberdorf. I am a lecturer at the University of Texas. I teach both general chemistry for majors and non-majors. These are my volunteers here. They are previous students of mine, so that's Kim and Jackie. Let's give them a round of applause for helping me out. All right, so today what I'm going to be doing is essentially talking about hydrogen burning from the perspective of a chemist versus the perspective of an astronomer, not an astronomist, I learned. It's an astronomer, okay? So let me give you a little bit of background about myself. Like I said, my name's Dr. Kate Biberdorf. You can call me Kate, Dr. B. You can try to get Biberdorf out of your mouth. I married into the name, totally fine. I understand if you don't want to say that, that's okay. So, like I said, I'm a lecturer at UT. I teach general chemistry. And so I have a PhD in inorganic chemistry. That's my favorite thing in the entire world. I have 4 different jobs at UT. My favorite one, aside from teaching you lovely ladies, is my outreach program, which is called Fun with Chemistry. So Fun with Chemistry is an outreach program. It's entirely funded by the Department of Chemistry. And all I do is I go out to local Austin schools and I blow stuff up. I do not teach them anything. I mean, I kind of do. I sneak science in there. But essentially, my entire goal is to get them to realize that chemistry is awesome. It is really, really fun. And you do not have to be a nerd. You do not have to be a freak. You can just be fun and like to blow stuff up and like to do chemistry. And so that's my goal. And you will see, especially when I get to this one right here, I really like my job. Okay. Last shameless little plug of mine. If you have students who are in elementary schools or middle schools or children of yours and you want me to come out to their school and do stuff for free, please contact me. It's funwithchemistry at utexas.edu. I'll be around all in the afternoon or evening. Also, if you are on Twitter or Instagram, please tag me in any pictures you have at funwithchem. Okay, moving forward. So like I said, we're going to talk about hydrogen burning. So my entire goal today is to talk about hydrogen burning in the context of either chemistry or astronomy. You're probably going to figure out what I personally like a little bit better than others, but that's okay. I'm going to do this with an open mind. Big thing is I'm trying to accomplish a goal here, and my main goal is that I want you all to understand the difference between a chemical reaction and a nuclear reaction. That is something that I battle the entire time, especially with incoming freshmen, is they think it's the same thing or they think they're interchangeable, and they just are not, okay? They're absolutely different. So by the end of this talk, hopefully you will have a better understanding of the difference between a chemical and a nuclear change. So because it's an astronomy lecture, we're going to start with astronomy. And so this is called the stellar hydrogen burning, also known as the proton-proton chain reaction. This is what happens inside of the sun. So it's also known as hydrogen fusion. And so for those of you who are not chemists and are freaking out because you don't know what any of this means, basically the only thing you need to understand from this diagram is that the subscript is giving you your number of protons. Your protons, or the number of protons, defines what type of atom you are, or it tells you what type of element you have. So for every single one of those that have a little 1 for a subscript, they are all next to a giant H. And so if you have 1 proton, by definition, you have to be hydrogen. You can't be carbon, you can't be palladium, you can't be Bill Nye, you are only hydrogen, right? Now, for number 2, by the way, my dream is to become Bill Nye, so I took that personally. So now for the second one, if you have a subscript of 2, it means you have 2 protons. So all the 2s, when you have a subscript of 2, it is next to an HE because by definition, you are a helium atom. So now, in the context of hydrogen burning inside the sun, this is a proton-proton chain reaction. So from my understanding of this, this is the reaction that occurs when you're in a star that has a temperature of less than only 15 million kelvins or something. Just to give you a frame of reference, right now we're at 298 and I'm sweating, okay? So 15 million is just absolutely very hot. So here's what happens. You have 2 protons, right? 2 hydrogens. They come together, slam together. You create something called a diproton, also known as helium-2. Immediately, you should be thinking, ooh, that sounds weird, that's very odd. That's because it has no neutrons to stabilize it. So if you have 2 protons in your core, in your nucleus, and no neutrons, that bad boy is splitting immediately, okay? So the first thing that happens is you go from helium-2, you immediately break apart, and you can either do one of two things. You could go backwards and go back to hydrogen, or you can morph into deuterium. Deuterium is an isotope of hydrogen. It has one proton, has to have proton because it's still a hydrogen, but it has one neutron, so that's deuterium. Now, once you have deuterium, you can have a proton capture, or you can hit it with a high energy proton. It can turn into helium-3. Now, here's the cool part. When you have one helium-3 and another helium-3 and you smash them together, you end up getting helium-4 and some other garbage. But helium-4, also known as an alpha particle, is extremely high in energy. So the entire purpose of this reaction is to go from a proton to a helium-4 or an alpha particle. Now, because I'm not an astronomer, I had to look this up. So the total energy for this in one cycle, just one cycle, is 26.22 mega electron volts. Now, this particular cycle occurs 9.2 times 10 to the 37th cycles in 1 second. Okay, that was 10 to the 37th in 1 second. So a very quick calculation, in 1 second, in the sun, it can create 3.86 times 10 to the 26th joules of energy per second. I mean, that's crazy, right? I cannot do a demo to show you that energy transfer. I mean, it would just be a disaster. So we're gonna have to wait till we get to the chemistry standpoint. But that's a lot of energy, and they've changed their identity. They started as helium, and they started as hydrogen, and they ended as helium, okay? All right, so now we're gonna jump up to a bigger star, so something bigger than the sun. This right here is a very, very simplified version of a CNO cycle, a carbon, nitrogen, oxygen cycle. So if you look at the very top, I have carbon-12 listed. So it has 6 protons and 6 neutrons. By definition, if you have 6 protons, you are called carbon. So we start off with a very, very stable isotope of carbon. What we do then is we hit it with a proton, and then it immediately adds that proton to its nucleus. So if you go from 6 to 7, you've changed your identity. You're no longer carbon, now you are nitrogen. Now, nitrogen 13, very unstable, very, very, very unstable. And so instantly, the second it turns into nitrogen 13, it undergoes a quark transformation, otherwise known as beta decay, and it converts a proton into a neutron. So you can see the 7 then turns into a 6. If you then turn into a 6, you have to turn into carbon, okay? You're no longer nitrogen. Now, we're down here at carbon 13. That's pretty stable. We hit it with a proton, it turns to nitrogen 14. Very, very, very stable. We hit that with another proton, high energy, and we turn into oxygen 15. Super unstable, super, super unstable. And so just like with nitrogen 13, it's like, oh, get out of here. Grabs its proton, turns it into a neutron immediately, and goes back to nitrogen 7. Now, I don't care if you didn't understand any of this, pay attention right now. This last step is the important step, okay? When you have nitrogen 15 and you go to carbon 12, the only way you could possibly do that is by hitting it with a high energy proton and releasing an alpha particle. That's the entire point of this process. If you do not release a high energy alpha particle, you might as well not even pay attention to this slide, okay? That's where the sun gets its fuel. It releases energy. The last one was 26.2 mega electron volts. This is something like 26.7. So even more energy, even more explosive. I definitely cannot do a CNO demo. All right, that's the astronomy side of it. So it releases a lot of energy. You change your identity, and we're talking about protons and neutrons only. Now for the fun part. Combustion. All right, so I want to start off with talking about combustion here. When I talk about hydrogen burning from a chemical standpoint, we are now talking about the potential energy of your electrons. We're no longer talking about protons and neutrons at the core. We're talking about electrons which go around on the outside. So when we talk about this from a chemical standpoint, we talk about blowing stuff up. And so what we're going to do is do this in terms of combustion of hydrogen. So let's start with hydrogen, and I also want to see helium so we can show both of them. Both of them right up. Go ahead and get in the orange one, Jackie. All right, so this is just like what you just saw, but just to give you a comparison. Now, I want you to think, is this 10 to the 26 joules of energy? No. Okay, here we go. Here's hydrogen. Okay, people in the front, can we feel it maybe slightly? Yeah. A little too much. Sorry, microphone. You could feel it slightly, right? So the combustion of hydrogen releases about 286 kilojoules per mole. That's it, 286. Not something times 10 to the 26 joules per second, right? This is 286, so it's a huge difference. A chemical reaction gives a tiny amount of energy. Now, remember the whole point of those last two slides were to take something like hydrogen and convert it to helium. So let's see what happens when we blow up helium. Haha. Okay, you ready? Okay, cover your ears. 3, 2. I tricked you. Okay. Helium is incredibly stable. That is the entire reason why this happens. It has 2 protons, 2 electrons, 2 neutrons. It is the happiest it can ever be. It is incredibly stable. It's inert. It's a noble gas. So when I try to blow up helium, it's like, gives me the finger. It doesn't care at all, okay? All right, so now what we're going to do is moving on. Why do we have a transfer of energy? How come the people in the front row could feel that when I blew up my hydrogen gas? Well, if we look at this, I'm going to use my candlestick here. We have a reaction progression. So on the y-axis, we have our energy, and on the x-axis, you have your reaction progression. So for those of you who are not chemists, when I use the words reactants and products, the best way to describe that is to put it in terms of baking. So if you were to make a cake, your reactants are going to be your flour, your eggs, your sugar, your chocolate chips, obviously, and then your product is going to be your cookies or your cakes. Does that make sense? Yes? Okay. So what you have to do in order to have a spontaneous or a favorable reaction is you start off with your reactants at high energy. Nature is always, always, always trying to get to a place of lower energy. It is more stable. If you think about this, you're never going to want to go outside and just hang on to the monkey bars because it takes energy. You're up high, you have to hang on. You'd much rather sink down into your couch, right? It's much easier, more stable. Nature is always trying to get to a place of lower energy. So these combustion reactions start off with your reactants, that's your hydrogen and your oxygen, at high energy, and then the whole driving force is that it can get to low energy, but it only releases 286 kilojoules per mole. Now, why am I telling you this? Well, if you have a combustion reaction and you release energy and something is sitting there waiting to gobble it up or eat it up, something really cool happens. Ladies, can I see my next balloons, please? So what I've done here is I filled these balloons with hydrogen gas, and then inside of them, go ahead and put it up there, inside of them I filled it with an inorganic salt. So I have something like strontium, potassium, sodium, and copper. So I'm going to start off on the edge. These are more of your fireworky type balloons. Okay. That's the word I'd use. All right, so this is strontium chloride to be specific. So we see the red. Yeah, I'll take applause. Yeah, let's do it. This is potassium. Oh no! That wasn't supposed to happen. Oh, that's right. All right, so pretend that was beautiful and purple. So now, I cannot do fireworks without actually doing a firework, okay? And now that it's up here, I'm going to drop it down just one little bit, just in case. I want to come back, okay? Let's drop that down. So what I've done here is I filled it completely with hydrogen gas, and then I put 2 scoops of magnesium metal in it. So if you've, yeah, that's right. Whoa! So this is essentially a baby firework, okay? If you want to tape it, this is probably the coolest one. Here we go. 3, 2, and 1. All right, so now I can't just blow stuff up, I gotta talk about it, right? Okay, so we'll really quickly talk about that. Essentially what happened, combustion reaction, a chemical change. So the electrons transferred, instead of being a hydrogen and a hydrogen connected, then it transferred and now a hydrogen and an oxygen are connected. So the electrons changed, they transferred, they moved, but we only released about 300 kilojoules of energy. However, hydrogen stayed hydrogen. It didn't turn into carbon, it didn't turn into Bill Nye, it didn't turn into anything else, right? Okay. So now what happened, combustion reaction, the inorganic salts were in there and it got all this energy and they're like, yes! And it's just like taking a shot of Red Bull. They shoot all the way up to the highest energy possible, they let go. As they slowly return down to the ground state, that's what we can see visually. So as it drops down, it emits off this radiation and it's gorgeous. Too bad you missed the purple one, right? Okay, so now, very last thing I'm gonna do, no, that's not true, two left. We're gonna see what happens when we increase the amount of hydrogen. So all I had there was just a little bit of hydrogen. Now we're gonna see what happens when we blow up that stuff you're drinking, the ethanol, the methanol, and isopropyl alcohol, ladies. So what we're gonna do here is we're going to take our liquids, come on up. So I need goggles and gloves, both of you. Okay, sorry, they're my old students, I can't help it. Okay, so now, what we're gonna do is we're gonna take our alcohol. So just so you have a frame of reference, methanol has a heat of combustion of about 700 kilojoules per mole, ethanol is at about 13, and then isopropyl alcohol is at about 2,000. So we're gonna see how that works. I only have like a glove and a half. That'll work. All right, are we ready? All right, so what we're gonna do, no, I'm okay. So what we're gonna do is I will talk you through this. So I'm gonna have to get off the mic, I apologize, but I gotta have gloves on for this. So what we're gonna do, ladies, go ahead and open up your small little can. You're gonna dump it in. So it's purely ethanol, methanol, and isopropyl alcohol. It's about 40 mils, but we're gonna say it's 20 because that's how we get in with the fire code. So it's 20 milliliters. Cover with your palm, cover with your palm, cover with your palm. There we go. All right. So what we're gonna do is turn it on this side and take a step back. Side, there we go. So what we're gonna do is we're priming our container. Priming our container just means we're coating it with the liquid. Now, when I first met Jeff was at a Thinkery 21 event and it was the best time this demo has ever worked. Why? It's because I called a wasted volunteer on stage and he got up there and he wasn't like this, doing this, no, he goes, yeah, yeah, yeah. So, okay, ready? We gotta do that. Here we go, here we go. 1, 2, 3. 3 rotations. 1, 2, 3. Over the table. Invert on your hand will get wet. That's okay. Once it gets wet, turn it right back up, palm on the top. Beautiful. Jackie, both hands. Cover mine, please. Yep, that'll work. Okay. All right. So what I'm gonna do here is I'm going to ask for the ladies to drop their hand and then run away, okay? This one here is methanol. You're just gonna step back, that's all you're gonna do. You're gonna stay nice and calm. Nice and calm. Run, run, run! This right here. All you're doing, Jackie, is you're going to take a step back. Okay, keep that hand covered. Do not run away. Don't run away. All right, this is ethanol, so we've just increased. Hand, hand. All right, now this one is isopropyl alcohol. Ready? Okay, now wait, okay. Go, go, go! I could go on and on and on about this, but I'm almost out of time, and so I'm just going to tell you chemical reactions, electrons were changed, and all of them stayed the same identity, yes? Okay, really quickly, which one of these, 1, 2, or 3, would you want to use to blow up a building? 3. Which one would you want to use to light your menorah to keep it light for 8 days? Beautiful, okay. 3, yeah, I like that. All right. So here's what we're going to do. I need to review the whole point of why I decided to blow this stuff up. The difference between a chemical and a nuclear reaction. 3 major differences. For a nuclear change, you are changing the identity. It all occurs with your protons and your neutrons. For a chemical change, everything happens with electrons. So it's completely different. They are not even close to the same type of reaction. Now, for a nuclear change, you're changing the identity of your atom. For a chemical change, you are not changing the identity of your atom. For a nuclear change, you're releasing on average 10 billion kilojoules of energy per mole. For a chemical change, it's like 500, okay? Big, big, big difference. From here on out, none of you are ever allowed to get those 2 mixed up. Deal? Yeah. Okay, so now because you were such a great audience, I'm actually going to do one more demo, but everyone in the front, you have to promise me you will do 2 things. A, stay seated, and don't you dare throw ethanol on me. I don't know why you would, but don't do that, okay? All right. I gotta get down there somehow. How do I get down? All right. Now remember, this is because chemistry is the second best science in the world. Ready to stay calm? You have to stay calm. Please do not rush me for any reason, okay? So what I'm gonna do, I'm going to take a blowtorch. I'm going to take cornstarch and I'm going to put it in my mouth. Yeah. You guys ready? Yes. Oh, that was disgusting. Okay. Thank you so much. You've been such a great crowd. My program is Fun with Chemistry. Contact me, call me, let me go entertain your kids. Thank you so much. Hook 'em horns! Good? You okay for Q&A?
All right, we have time for a couple of questions. Down here in the front.
Okay.
Chemical reactions generally use mass. Is there any reactions and products the same mass or not?
No, but there is a law. Sorry.
Could you repeat the question as
Thank
well?
you. Yeah, I was just going to do that. Thank you very much. So you're asking essentially, is there a mass defect in chemical reactions? The answer is no. We must obey the law of conservation of mass and matter. And so in theory, I mean, again, this is all in theory, right? In theory, we have 100% of the same mass on the other side. And so we have to balance our chemical equations, and we just make sure that we are never losing matter, losing mass. In theory, we never lose it. In a nuclear reaction, the change in mass is definitely the result of all that energy being transferred. That's lovely. I love that you know that. Oh, another one. Okay.
All the times you've done that,
Yeah.
none of your opinions has ever slipped a little aluminum cornstarch.
No. No, but I have set my hair on fire on TV. I didn't really tell you that. But yeah, I have a monthly TV segment on We Are Austin. It's actually tomorrow, so check it out at 9 a.m. But it's the third Wednesday, and the first time I did that demo was on TV, and I set my hair on fire. I handled it like a champ, but afterwards I was in tears, man. That was awful. What else? Anybody else? Yes, sir.
So on the last balloon on stage,
Yes. Magnesium. All I did was put magnesium in there, and so magnesium has access to d orbitals, and so it has a higher energy gap that it could possibly reach. And as it comes down, that huge transfer of energy, it releases off that beautiful, beautiful, sparkly energy. Yeah.
Okay, there's one way over the side here.
Yes, sir. Cornstarch, don't do it, it's awful. Quick thing with that though, if you ever do decide to become a circus freak like me, make sure it's solid. It must be solid in your mouth. Don't ever put liquid. People put ethanol or Everclear in their mouth. Don't do it, it's volatile. The second it comes out, that flame can come right back. You have to use solid, just spit it hard, won't be a problem.
Is this where we should say, don't try this at home?
Yeah, don't do it unless afterwards.
Okay, there's one more on the stairs over here.
Yes, sir. Okay, so the reason I use an inorganic salt, it has to do with solubility, and it all has to do with the fact that in order to get the salt into the balloon, I have to dissolve it. And so I dissolve it in either a water mixture, methanol mixture, and then I use like a squirt gun essentially to squirt it into the balloon, then I fill it with hydrogen. An organic salt is an oxymoron, you can't really have that, but I don't expect you to know that yet. It's the difference between covalent and ionic bonding, if that helps. We'll talk later.
All right, let's thank Fun with Chem again.